Greetings, my name is Barry Setterfield. Welcome to this session. In the first session we discussed the fact that our solar system probably had 10 planets originally. 2 of those planets exploded and the reasons for the explosions were discussed, and we'll be talking about that a bit more in this session. Those explosions sent debris right throughout the solar system, hitting the moons and the planets and leaving craters covering their surfaces. Now, most of the debris, or a lot of the debris, is still there in the original orbits, or close to the original orbits of those 2 planets. So we have 2 debris belts in our solar system. One is between Mars and Jupiter, the asteroid belt. The other is out beyond Neptune. This is the Kuiper belt. So the subject of this video is the timing of these events. When did this all happen? When were the craters formed? When did the explosions occur? And what was the outcome? There is a surprise right at the end of this session, so stay tuned. So let's get started. There are 2 ways of dealing with time: relative time and actual time. Relative time means that we can see if one thing had to happen before another did. For instance, there are very wide dark areas on the Moon called Maria, and overlaying them are many craters. This particular one is Mare Imbrium. The bright crater at the bottom is Copernicus. Obviously, the Maria had to have formed before the craters on top of them were formed. This is relative time. There is another way of determining relative time: cosmic ray impacts. Cosmic rays of high-energy protons and atomic nuclei from distant galaxies, from our own galaxy, and from our Sun. They are energized by processes such as supernovas and can accelerate to speeds close to the speed of light. Everything in our solar system is exposed to these cosmic rays, and they leave tracks on the surfaces of the objects that they hit. The more tracks, the longer that object has been exposed to cosmic rays. This is a microphotograph of a portion of an object from the asteroid belt. It shows the tracks left in the crystal structure as the cosmic rays hit. Some of these nuclear tracks, as they are called, are shown by arrows, but a number of others can also be seen there. The 2 planets which exploded would have each collected numbers of cosmic ray tracks on their surfaces before they exploded. After they exploded, the pieces would then collect other tracks on their newly exposed surfaces. Here is an enlargement of a typical cosmic ray track as it comes to a stop in a crystal matrix. The time elapsed since the breakup of the parent body is given by the number of such nuclear tracks which are on parts of the fragment which were not on the surface of the original planet. The more tracks, the longer the time. The cosmic ray bombardment of host material also produces radionuclides, that is, radioactive isotopes of elements. These are found in meteorites and asteroids, but are difficult to obtain by mechanisms other than cosmic ray bombardment. These radioactive isotopes, similar to those shown here, have known half-lives, and the products can be analysed to give us atomic dates. These atomic dates are absolute dates, not relative time. In other words, they give an independent assessment of the atomic date and the order in which things happened. With the asteroid and Kuiper belt objects, the clock starts ticking once the breakup occurs. It is important to remember, however, that the surface of those planets had already been affected by cosmic ray impacts. Cosmic rays may penetrate to a depth of 3 meters, as shown in green here, and below that there will be a zone, here shown in grey, where radioactive elements are more concentrated. This will give the radiometric or atomic age of the unfragmented parent planet. After the explosion occurs with the initial fragmentation, the interior pieces give younger cosmic ray exposure, or CRE ages, than the original surface. In fact, ongoing fragmentation events give progressively younger dates as those pieces become smaller asteroids and even smaller meteorites. So we look at the older concordant dates on these fragmented bodies to give us the atomic time of the original breakup of the two planets. The last bit of foundation needed is to remind those who have followed our earlier videos that atomic time is not the same as orbital or gravitational time. Those earlier YouTube sessions have fully discussed the issue. Atomic time depends on the speed of atomic processes. Since atoms are made up of charged particles, they depend on the electric and magnetic properties of space. This diagram may be a help. As the universe expanded, the electric and magnetic properties of space changed. It meant that all the electric and magnetic field strengths became less and currents slowed down. This then required all charged particles to move more slowly. As a result, all atomic clocks ticked more slowly. God tells us in the Bible in Genesis 1:14, on day 4, to note our time by gravitational phenomena, the sun, the moon, and the stars. Gravity is a constant through time. 1 year is determined by how long the Earth takes to orbit the sun. Our view of the stars is determined by where we are in relation to the sun. This is a constant. Since we have astronomical data on the rate of expansion of the universe, these same data give us the rate of ticking of atomic clocks back to the origin of the cosmos, shown in this curve. In the beginning, atomic clocks were ticking extremely fast. The rate of ticking then dropped off very rapidly. Finally, the rate of ticking tapered off to what we have today. This data curve allows us to correct atomic dates in astronomy and geology to actual orbital dates. The times given through the middle of this video will be the standard atomic time used by science. But near the end of this session, we will show you the conversion. The result is something very interesting that accords with Scripture. We had no way of determining absolute dates on the Moon until Apollo astronauts brought back lunar material for radiometric dating. The landing sites in the numbered Apollo series are marked here. Most of the material they brought back was from the Maria, the large dark areas which were obviously formed before the craters that pockmarked them. The radiometric dates for the Maria cluster around 3.9 to 3.2 billion atomic years old. Some are younger, about 2.9 billion atomic years. The impacts which produced the Maria were incredibly severe. We know this because they hit with a force and to a depth that caused melted moon rock to fill the huge impact craters and spread that magma across the surface of the moon. That is why the Maria are dark. The crater size also indicates both the force and the size of the impacts. One of the largest examples is Mare Imbrium, shown here. The molten rock flooded a circle 1,000 kilometres wide between the mountainous borders, which are up to 2 miles high. The magma then overflowed out across the area below and to the right of Mare Imbrium in this image, the blue arrow. All told, it has been estimated that 1 million cubic miles of magma is involved. Up to 1,500 kilometres from the explosion centre can also be found linear features, the orange lines, extending along great circle arcs that intersect in Imbrium. Some result from flying debris, and others from large movements of the moon's surface on a radial fault system caused by the explosive impact. The circular Maria, including those here, are mainly found in the northern hemisphere of the moon, and all had a similar origin. Since their atomic ages are all within the same range, it is apparent that they are produced by a whole series of early impacts. This cataclysmic event is referred to as the Late Heavy Bombardment, or LHB. Why don't we see that kind of impact force with the later craters? It is generally agreed that the LHB, the Late Heavy Bombardment, was the result of impacts by materials from the outer solar system, material from where the Kuiper Belt now is. The speed at which these objects impacted was so great as to drive them deep under the surface of the Moon. Why would Kuiper Belt objects hit with greater speed and force than objects from the asteroid belt? There is a somewhat complex technical explanation in physics, but I think a more simple explanation will do. You know that here on Earth, the higher something is when it starts to fall to Earth, the harder it hits. Drop a rock from a foot off the ground and it's no big thing, but drop it from 1,000 feet off the ground and the force is much, much more. The Sun is the centre of gravity in our solar system. The Kuiper Belt objects are coming in towards it from quite a farther distance than the asteroids. Therefore, the speed and impact energy they pick up as they keep going is tremendous. Indeed, for any given mass, as the velocity of impact increases, blue labels, the impact energy and pressure increase much more, green labels. If the velocity doubles, the energy quadruples. Objects from the Kuiper Belt can have a maximum speed of 45 miles per second. This is quite different from the 10 or 15 miles per second the objects from the asteroid belt can achieve. With the Kuiper Belt, high impact speeds and energy, the volume of melt, the red labels, goes up quite significantly. In fact, it goes up way beyond the standard equations levels for asteroid belt impacts. What is happening is called decompression melting. A.P. Jones and his team's computer diagram shows the situation 40 seconds after impact. There is a transient or temporary cavity about 60 miles across and a pressure pulse up to 3 million atmospheres, shown in red. That has propagated as a shock wave, followed by a release wave of decompression, blue, that has gone over 250 miles, that is over 400 kilometres, into the crust and mantle. Sometimes this pressure pulse goes right through the planet. This is true for the Earth, the Moon, or any planet. Following the impact, the resulting high temperature and sudden release of pressure on the crust and mantle mean the rock melts. When the rock melts, it gains 10% in volume, so it may have erupted out onto the surface of the Moon as an initial tsunami. William Van Dorn in Oceanography in 2014 suggested that on the Moon, the wave of magma may have been well over a mile high. The flood of magma formed a large maria, or what the early astronomers thought were seas of water. We have craters on Earth, but nothing like that. There are no craters on Earth that date to that age. The general agreement is that later events eroded away the evidence of those impacts. However, we may have the results of those impacts that still remain. When the Earth was hit by the late heavy bombardment impactors, at the same time the Moon was, the magma volume created by those impacts could have been 500,000 cubic miles or more. This is in accord with the hydrocode computer modelling. On Earth, these impact pressure pulses penetrated well over 400 kilometres into the mantle, forming great magma plumes which rose to the surface. They ensured ongoing volcanic activity for some time after impact, as the plumes rose under the early crust and then solidified. That result would be similar to the plume now under Iceland. That plume is shown here to a depth of 400 kilometres. The extensive melting decreased the density of the plume and increased the rigidity under the cratons, making these areas more stable. The outcome is that this ongoing volcanic activity destroyed the impact crater and the top layers were removed by later erosive processes. All that was left were the large regions of granites and metamorphic rocks. These are the purple areas here on this map. They became the stable cores of our continents and are called cratons today. The Bible calls them the pillars of the earth, which has produced much mockery from those who don't know what the Bible is talking about. Before we move on, let's summarise what we've found to this point. Because of its apparent absence on Earth, the late heavy bombardment was first discerned from the Moon. The great dark subcircular maria there were dated atomically by samples obtained from the Apollo astronauts. The generally circular nature of their borders and other features indicate an impact origin, but the huge magma overflows indicate it was high-speed objects which impacted. Thus they must have come from the outer solar system's Kuiper belt. The atomic date of impacts range from 3.9 down to 3.1 billion atomic years. This is in line with the 3.9 to 2.5 billion atomic years for the cratons on Earth. This gives us a good atomic date for the explosion of the Kuiper belt object. Very few other lunar features have been dated by the atomic clock, so instead of an absolute age, a relative age is assigned by using 1. Superposition of objects, and 2. Crater counts. Superposition may be illustrated by the region at the edges of both Mare Imbrium on the upper left and Mare Serenitatis on the right. The red arrows follow the ridges and grooves radial to Imbrium, which intrude onto Serenitatis, showing that Imbrium was formed later. The other method of dating used for the rest of the solar system employs crater counts. But even here, there is an interesting problem where the standard theory disagrees with the actual data. The standard theory is that the impactors were leftovers from the formation of the solar system. This process is assumed to be gravitational, in which the disk of material circled the Sun and underwent collisions. These collisions gradually built up the planets, which eventually swept up the particles in their orbits. It's then assumed that cratering was at a maximum at the solar system's origin and then tapered off to a steady rate. Since pre-Apollo days, this was the standard astrophysical explanation for what we see. As a result, the graph presented by standard astrophysics regarding numbers of impacts looks like this. A high number of impacts are at the very beginning on the left and then tapered down to a steady rate to the current date on the right. But that's not what the data show. The data show that the impactors are not the leftovers from solar system formation. Instead, they form a pattern of 4 breakup events which show spikes in the actual graphs, like this. We now begin to examine the data that leads to that conclusion. The planets have heavy element cores that were radioactive from the first. So it is not hard to understand that the frozen planet beyond Neptune exploded all at once when the heat melted and thus expanded all the frozen gases in its mantle. However, the data show that the asteroid planet had something else involved. It did not explode all at once, but in 2 distinct stages. Then its moon exploded some time later. Our previous session indicated that there is an increasing amount of water or water ice on the planets as one goes out from the Sun. This conforms to the plasma model. In there, Markland convection in plasma filaments sorts the elements. So the rocky planets had water in their mantles and surface. The gas giants had water, ice and rock in their giant cores, and the ice giants had huge water ice mantles. The data indicate the original asteroid planet between Mars and Jupiter had up to 13.5% water in its rock and mineral structure, and its moon had up to 22%. The Earth has at least 2 to 3% locked up in minerals in its mantle, so there is over 3 times the volume of all of our oceans down there. To understand why, one of the dominant mantle minerals on Earth is olivine, shown on the left. But olivine is the dry form of the mineral. It has been found that there are a number of hydrated forms of olivine in our mantle. One is the mineral serpentine. Another of interest is ringwoodite, shown here from a microscope on the right. This type of olivine forms a key segment of the mantle. This mineral has absorbed water in every possible way, so it is part of its structure. In the lab, when these minerals are heated, they give up their added water and become olivine. Thus, rapid radioactive heating of planetary interiors, like the asteroid planet, drove out this water. The water then built up under the planet's crust and exerted increasing pressure on it. As a result, in Part 1, we saw evidence that Venus had flooded, Earth had flooded, and Mars had flooded. Professor James M. Dom from the University of Arizona pointed out that the outflow channels on Mars, shown here, were part of a system carved out when 1/3 of the volume of the Indian Ocean was outpoured in 8 weeks to form the Northern Ocean on Mars. And the asteroid planet might have flooded too, except the evidence is that something else happened to it. It got hit, and hit hard, probably by something from the Kuiper Belt. The reason we think this must have happened is because the oldest remnants we find from that planet are not from its crust, but from its core. Let's examine the evidence. Cosmic ray exposure ages of fragments from the asteroid belt give the initial breakup times of parts of the asteroid parent planet and its moon. The progressively younger dates give later fragmentation events, as we have noted. Oyster et al. Have presented 18,000 data in the article in this book. From those data histograms, the oldest atomic dates for the successive breakup of the original asteroid planet were found. Among the 3 main groups of asteroids and their associated meteorites, the metallic or iron group, graphed here, have the earliest breakup times, and those times are marked by a red star for the 9 types involved, giving an average of 770 million atomic years ago. Noble gas analysis indicate that the parent body first broke up about 810 million atomic years ago. The histogram data suggest that the fragmentation event peaked about 650 million atomic years ago, shown by the blue stars. The conclusion is the breakup of the metallic parent body, the core of the original planet, probably occurred between 810 and 650 million atomic years ago. The varieties of stony or silicate asteroids and associated meteorites, including the stony ions, can be treated in a similar way. They indicate a breakup age of the parent body, the silicate mantle of the asteroid planet, of about 258 million atomic years. Likewise, the 12 classes of carbonaceous and chondritic objects give a consistent breakup time for the parent body, the asteroid planet's moon, about 65.8 million atomic years ago, with a spread of results of about 15 million atomic years around the average. These results were reviewed and published in the conference monograph for the Natural Philosophy Alliance in 2013, Chapter 9, Cosmic Ray Exposure Ages and Solar System History, page 319 and following. To any geologist who has studied Earth history, these breakup times are important. The geological strata on Earth consist of 4 eras separated by 3 catastrophes which wiped out many life forms and changed the climate. Impacts are implicated in all 3 cases of the catastrophe. The earliest of those eras, shown at the bottom of the geological column here, is called the Archaeozoic or Precambrian. It effectively ended with Catastrophe 1, sometimes referred to as Snowball Earth event. This is placed within the limits of 810 to 620 million atomic years ago. The following Paleozoic era ended with Catastrophe 2, the Permian extinction, 250 million atomic years ago. The Mesozoic era which followed ended with Catastrophe 3, the KT extinction, or Cretaceous Tertiary extinction, about 66 million atomic years ago. The role of impact in these catastrophes will be discussed in detail later. However, let's return to the asteroid planet and how the cosmic ray exposure data show it was the core that blew out first. How is that possible? It is true that the core was radioactively heated, as was the mantle, but the mantle pressure was effectively stopping the core from exploding. What released the pressure on the core of the planet that was many hundreds of miles in radius? Remember how the late heavy bombardment impactors caused the Maria on our moon. Only a Kuiper belt object could have penetrated deeply enough into the asteroid planet to cause the pressure on the core to be released and the molten iron and rock exploded outwards. The mantle above the core still had radioactive elements in it which continued heating the rocks with a high water content. But the planet was now weakened. As the heating continued, the water was turned to steam and the rock melted, the entire planet disrupted with explosive force about 255 million atomic years ago, according to cosmic ray exposure data. That left the asteroid planet's moon, which had a chondritic composition. That is to say, it was made up of more or less rounded mineral grains like the one in the centre on the left. These grains were produced by plasma processes and cemented together in a matrix which contained up to 22% water. The water was released by radioactive heat and chemically reacted with the grains. The right image shows the grain disintegrating and the dark band of chemically altered material around it from the action of hot water. In contrast, the grain in the left image is sharp and unaltered. This action of water weakened the structure of the whole moon, so it was unable to stand the pressure from steam and the melting of some of its metal and rock core and resultant expansion. This led to an explosive disruption. We can date that breakup from cosmic ray exposure data as about 66 million atomic years ago. That's basically the testimony of what happened and when from the asteroid belt, the Kuiper belt, and the atomic data from our own moon. But although the late heavy bombardment was well established, there is nothing from our moon to back up the cosmic ray exposure studies of the breakup of the asteroid planet and its moon until recently. Instead, the timing of the cratering events throughout the entire solar system was based on the lunar studies. These studies came from crater counts and the curve of expected fall-off rate of impacts after solar system formation is shown here. Thus, the results of asteroid studies of the cosmic ray exposure ages remain theoretical, with no proof from the moon. However, in 2019 and July 2020, different methods were employed to find when lunar craters were formed. These methods changed the discussion. The first of these was used by Sarah Mazrui and her colleagues in 2019. Infrared data from Lunar Reconnaissance Orbiter gives the heat emitted from rocks in craters and the depth of dust over the rocks. The rocks break down into dust at a rate that can be checked from craters that have already been dated atomically. The Maria and associated features gave the spike in impact rate from the late heavy bombardment about 3.5 billion atomic years ago. This new method revealed another spike in the impact rate occurred about 290 million atomic years ago. This is very close to the second break in the asteroid belt at 258 million atomic years from CRE ages. And the Permian extinction occurred on Earth at the same time. So Mazrui et al. Linked the lunar and the Permian results. Yet we can go further. Here is some of the data in colour-coded form. They examined 110 lunar craters with diameters from 5 to 60 miles. The blue-coloured craters were formed between 870 and 580 million atomic years. This is in accord with the CRE cosmic ray exposure data of the first breakup in the asteroid belt between 810 and 650 million atomic years. Then the Mazrui team noted a gap between 580 and 290 million atomic years with little impact activity. Then a spike and subsequent taper near 290 million atomic years, the green-coloured craters, occurred. Finally, the craters coloured yellow came down to the present. Cosmic ray exposure data hints that they may be from another spike near 65 to 70 million atomic years. This 2019 research received unexpected support from another team led by Kentaro Terada, who reported on the 21st of July 2020 in Nature Communications. They used data from the Selene Kaguya terrain camera to investigate the formation age of 59 craters with diameters greater than 20 kilometres on both the near and far sides of the Moon. As a sample of their results, this map shows in red 8 craters which the data indicate formed at the same time as the crater Copernicus. The 58-mile crater Copernicus is seen here from orbit. It is 2.4 miles deep. The team concluded that there was a spike in the number of impacts about the time that Copernicus formed. The weighted mean of their atomic age is about 658 million atomic years. Other determinations give atomic ages ranging up to 797 million atomic years. This is in close to the overall age range as quoted for the CRE data. The authors conclude that this meteorite bombardment spike occurred across the whole Moon, possibly due to asteroid disintegration. Indeed, from the lunar data, they suggest that impactors totaling some 30 to 60 times the mass of the Chicxulub event on Earth struck the Earth immediately prior to the Snowball Earth period, at the same time as Copernicus was formed on the Moon. This study thereby links lunar crater formation with Snowball Earth. So the accumulated data show there were 4 major times when the flux of impactors swept through the solar system. The result was anticipated on this graph as shown before. First, there was the late heavy bombardment climaxing around 3.5 billion atomic years. This came from the breakup of the Kuiper belt and formed the dark maria on the Moon and the Archean cratons on Earth. After a lull in activity, the first breakup of the asteroid planet occurred, with the flux peaking sometime between 800 and 600 million atomic years. This formed the craters associated with Copernicus around the Moon, as determined by the Selene data. This is about the same time geologically as the Snowball Earth strata formed on Earth. That was followed by the second asteroid planet breakup about 255 million atomic years ago, which gave an impact spike picked up in infrared data from the Lunar Reconnaissance Orbiter. This spike is coincident with the Permian extinction about 251 million atomic years ago. Finally, the disruption of the asteroid planet's moon about 66 million atomic years ago resulted in the Cretaceous Tertiary or KT extinction that wiped out the dinosaurs and formed the final suite of craters on the Moon. Now let us get back to the problem with the standard cratering curves shown again here. If these curves are valid, it means the vast majority of impact craters must have been completed very soon after the late heavy bombardment 3 billion atomic years ago. If this curve is true, only a few events like the formation of the craters Copernicus and Tycho could have occurred after that. But that is not what the data from the solar system tells us. That data says the real curve should take account of the 4 spikes in the cratering rate shown by the green blocks here. The first spike after the solar system origin was the late heavy bombardment from the Kuiper belt, shown by the green block on the left. This fits the date range from 3.9 to 3.1 billion atomic years. The other spikes or blocks on the right come from the threefold breakup of a planet and moon that gave rise to the asteroid belt. It is here that the third dot from the right gives data from the Copernicus group of craters. The second asteroid breakup was 258 million atomic years ago from CRE ages. This is confirmed by infrared studies of 110 lunar craters, giving the second dot from the right. This is coincident with the Permian extinction on Earth. Finally, at the extreme right is the dot representing the age of the crater Tycho. Tycho is the centre of a prominent ray system. The crater is 53 miles wide and 3 miles deep, and its rays go across the Moon. The Selene Kaguya study included Tycho in its assessment. Depending on the modelling used, that study concluded that Tycho had an age between 58 and 70 million atomic years, with an average age of 64 million atomic years. CRE cosmic ray exposure data suggested it may have been from a flux of material from the third asteroid breakup event at 65.8 million atomic years. Therefore, since these 4 events have been dated, it should now allow an atomic age to be assigned to a sequence of events that had only been relative before. We have the relative sequencing, that is valid. It is the timing that now needs to be re-examined. For example, all agree that the impact which formed the lunar mare orientali occurred after the Imbrium event. But how long after? Note the Orientali basin in the upper right here. It is 580 miles wide and has several rings with some central solidified magma. This formation is larger than many great circular plains, except Imbrium, but the whole structure is not flooded with magma as those other great circular plains have been. Why not? One reason we saw earlier could be that the impactor did not have high enough speed. If not, then it did not come from the Kuiper belt, as they are the only objects which have enough speed to produce the needed flow of lava. Thus Orientali may not be a late heavy bombardment formation on some 3 billion atomic years ago, but rather it may have originated with the first breakup of the asteroid planet about 800 to 600 million atomic years ago. Thus, a rethink of the actual timing of events may also be needed. This is important as other planets have similar structures. Here we see examples of the so-called peaked ring craters from Mercury, Venus, Mars, and at the bottom, Earth. The one in Canada is only 22 miles across. The one in Mexico is about 150 miles across, as determined by seismic and drilling data. All of them have several rings and a layer of magma which is solidified, but these structures are not flooded with magma as Imbrium is on our Moon. Furthermore, their location, relative timing, and other data indicate all were formed after the late heavy bombardment, but from separate asteroid breakup events. Therefore, for low mass and low velocity impacts, a simple bowl-shaped crater forms. For medium mass and velocity, a complex crater with a central peak and terraced wall forms, with a small melt layer on the floor. Finally, for large mass asteroids, with velocities up to about 15 to 20 miles per second, a peak ring crater forms with several rings and a thick melt layer. However, for massive Kuiper belt objects with very high velocities, the depth of penetration causes decompression melting, which forms a huge overflow of magma like Imbrium. Let's now apply all these principles to the rest of the solar system. Up until now, our Moon only had a few absolute dates to guide us, but it also had many relative dates from crater counts. This lunar standard has been used to assign dates and ages throughout the solar system. For example, on Mercury, magma from radioactive heating of its interior poured out through expansion cracks and resurfaced the planet, forming the old intercrater plains. Then came the late heavy bombardment, where a multitude of craters from electric discharge machinery, EDM, most less than 10 kilometres wide, peppered the intercrater plains. A segment is shown here with a large numbers of very small craters which can be seen at the bottom left quadrant. Craters with rays on the right are from later impacts and are not of electric discharge machining origin. This map of relative events on the planet Mercury is based on the lunar standard, yet it is still valid in the new fourfold breakup model. Observe that the pervasive violet background represents the old intercrater plains. The late heavy bombardment impactors form the bright blue craters and the huge northern smooth plains in light yellow, just like the lunar maria. Then the first asteroid-planet breakup gave impactors which formed the green craters and the large Callisto basin with its concentric rings of mountains like the Orientale basis on the Moon. Colour differences around the edge of Callisto are due to differing crater density from preferential EDM action during and after impact. The second and third asteroid breakups gave the dark purple and brown craters respectively, so the basic order of events on Mercury fit in with the new model. Only the old timing needs revision. In the inner solar system, Venus had a resurfacing event perhaps as late as 300 million atomic years ago. This has covered all the older structures, and it's difficult to date what is left. That leaves the planet Mars, whose order of events from the bottom up is summarised in this diagram, modified from standard astronomy. The first event is the impacts forming the lowland basins and other craters. The second is the Hellas basin and the craters from that event. The third and fourth are the Argia and Isidis basins and associated craters and features. The first event formed the deep northern basins, the big circles in the blue lowland areas here. They are equivalent to the circular mare plains on the Moon and the smooth plains on Mercury. In each case, the largest impactors mainly hit in the northern hemisphere and had a huge magma overflow. This is a characteristic of the largest high-velocity objects from the Kuiper Belt, which caused the late heavy bombardment, LHB. Here is an elevation map of Mars. Blue is depth, red is height. On our model, these LHB impactors resulted in huge magma overflows forming the lowland plains, labelled 1 here. But that is not the case for the other three basins. That is, despite the fact that the largest, Hellas, is 1400 miles wide and 5 miles deep. This confirms they are not from the LHB impact, but came after. Indeed, the data show the order of formation is 2 Hellas, then 3 Argia, and 4 Isidis. This model indicates basins 2, 3 and 4 probably came from asteroid belt breakups, in line with similar data from the Moon and Mercury. Only the old timing needs revision. These conclusions tend to be confirmed by details in the ejector blankets of these 3 later basins, of which portion of the Hellas blanket is shown here. Some craters are buried or partly buried. They were thus there before the Hellas impact. This indicates they were formed during the late heavy bombardment, the key event prior to Hellas. The clean, sharp craters on top of this blanket probably came from ongoing Hellas-related impacts and/or its electric discharge machining, which often produces flat-floored craters, which can be seen here. Looking at the ejector blankets and craters on the 2 later basins, a similar order of events can be traced. So this fits in with asteroid breakup timing. In the outer solar system is Jupiter's moon Callisto, which is almost as big as Mercury. Recent data suggest it has a deep, viscous, salty ocean, starting some 100 to 150 miles below the ice crust. As the radioactive heating of Callisto's ocean went on, it melted the bottom of the ice, so the ice crust got thinner. If the crustal ice layer is thin compared to impact depth, then a large impact will fracture the ice extensively into the series of concentric faults. This clearly had to happen after the ice crust had partly melted. Thus the 6 craters on Callisto with these multi-ring features all formed late. The oldest period is that of the cratered plains and their associated features. Then there were the light plains, followed by bright smooth plains, and finally dark smooth plains and their associated features. Let's look briefly at these 4 periods in Callisto's history. They give this standard order of events, but the timing may now need adjustment. The oldest surface is the cratered plains made up of ice and rocky material. It's heavily cratered, as shown on the left, and has an ancient structures like tinder in the centre, some quite large. It is also covered with small craters and pits that give evidence of electric discharge machining action, shown on the right. All this activity dates from the same time as the LHB impactors. On top of these ancient formations are the light plains with old and newer craters. The plains themselves are circular or oval and are part of the floors of large craters. The oldest large structure is Asgard, about 1,000 miles wide, part of whose floor is shown here. These formations correspond to those from the first asteroid Breakup. Younger than the light plains are the bright smooth plains, which are heavily fractured and have not been resurfaced. They are associated with several large ring systems. Their origin links with the second asteroid Breakup. But younger than all of these, as indicated earlier, is the 300-mile wide central crater of Valhalla, outlined on the left, and its multi-ring system, 2,300 miles wide, shown there. The crater rim and immediate surrounds of Valhalla have smaller craters and pits from electric discharge machining activity. In association are the dark smooth plains. They are called dark as they have a carbonaceous deposit on their surface, as seen on the right, which makes the leading face of Callisto in its orbit darker than the trailing one. Interestingly, Valhalla also has this material as part of its structure. The final breakup in what is now the asteroid belt was the planet's moon, which had a carbonaceous composition, so we would expect to see the evidence of that. We have seen that each planet has had an essentially similar catastrophic history and timing as a result of events in the Kuiper and asteroid belts. Essentially, there have been 4 occasions when impactors, planetary debris, and enormous associated electrical effects and machining swept through the solar system, scarring planetary and moon surfaces with craters. Basically, this was 3.5 billion atomic years ago, then about 800 to 600 million atomic years ago, next 250 million atomic years ago, and finally about 65 million atomic years ago. To any geologist, these atomic dates raise interest at once. As indicated earlier, each of these 4 catastrophes had their geological counterpart on Earth. Thus the LHB, the late heavy bombardment impactors, resulted in the cratons, which form the cores of our continents. These impactors were from the Kuiper Belt explosion, which happened very early in the history of our solar system. Subsequent events eroded the surface features of impact, leaving mantle plumes, granites and metamorphic rock emplacements as the only evidence. It is admitted that these granites are sodium-rich and grey, and essentially occur here only in these Archean cratons. The deep late heavy bombardment impact method of forming these features may explain why. But there's one other fact about the cratons which may support this impact origin for them. Markland convection shows that on Earth the element carbon was concentrated in a layer, shown blue here, 400 to 600 kilometres below the surface. The world's diamonds are also found only in these cratons and only come from those depths. Only late heavy bombardment impacts occurred at the time cratons were formed, and only LHB impacts give high pressure pulses up to 3 million atmospheres to that carbon-enriched layer. Diamonds are a high-pressure form of carbon, so diamonds and impacts may be related. The impact origin for diamonds was shown to be viable by an international team based at Goethe University in Frankfurt. They pointed out in Science Daily for September the 29th, 2020, that diamonds are formed by impact in carbon-rich strata. A key additional point in our case is the fact that the craton diamonds had to come up from those depths at well over 100 miles an hour, or they would have dissolved. Only the gigantic magma surge to the surface after impact decompression consistently explains how, and is depicted here. Many questions regarding other elements included in diamonds may now be answered. The catastrophic ending to the Archaeozoic is the Snowball Earth strata, dating variously from 800 million down to 630 million atomic years. Among the events of that time was the MAPSIS, MAPCIS, massive Precambrian impact structure in the Australian interior, whose extent is shown here. On the left is the raw satellite image. The structure is outlined on the right. Around the Earth, water under pressure from Earth interior burst out, shown on the left, carrying a jumble of pebbles, rocks and boulders for miles in a way which is often seen as coming from glaciers, hence the name Snowball Earth. 3 examples of this jumble of rocks come from locations around the world. From the top right clockwise we have America, Africa and Australia. The breakup of metallic or iron asteroids at 810 to 650 million atomic years fits this timescale very well. Only tectonic uplift after impact survived this erosive episode, like the MAPSIS ring structure. The following era, the Paleozoic, ended with the Permian extinction 251 million atomic years ago. As part of that event, a 300-mile wide impact crater was formed in Antarctica, the red spot on the left image, with the mass concentration circled in the white on the right. Mass concentrations accompany impacts. The Antarctic impact was so strong that it caused 3 million cubic miles of magma to be outpoured at the antipodal point of the Earth. The region covered by this magma is outlined on the map on the top left. This lava is now known as the Siberian Traps, shown on the bottom. The image on the right shows the thickness of the traps. From the mountain tops to the bottom of the valley in this image is about 1.5 kilometres. The date of this outpouring coincides with the Antarctic impact and the breakup of the stony or silicate asteroids peaking at 258 million atomic years. So all the data agree. The following era, the Mesozoic, ended with the KT extinction some 66 million atomic years ago. 8 large asteroid pieces hit at the locations marked by a star on the left map. One hit was from a 10-mile wide impactor, which made the 150-mile wide crater in the Yucatan in Mexico. That crater was pictured earlier, and its location is shown on the right. The breakup time of chondritic-type asteroids occurred between 80 and 55 million atomic years, and peaked at 65.8 million atomic years, near the time of the KT wipeout. The Mexican crater is strongly suspected of having been formed by a chondritic object, so astronomy and Earth geological data agree on the impacts from 4 breakup events. Up until now, we've been discussing everything in terms of atomic ages. So how could this possibly coordinate with anything in the Bible? If you have seen our previous videos, you probably know how this ends. The run rate of atomic clocks depend on the electric and magnetic properties of the vacuum. Atomic clocks have been measured as slowing compared with orbital time. For example, when astronomical events for the planet Mercury were timed by both orbital and atomic clocks, this graph resulted. It shows that the run rate of atomic clocks is slowing when compared with orbital time. This is not unique, Similar graphs for other objects show that the effect is general. The slowing can be shown to be due to the expansion of the universe. The expansion changes the strength of the zero-point energy, or ZPE, which controls the electric and magnetic properties of the vacuum. This has been fully discussed in other sessions. When all the data are put together, the rate of ticking of atomic clocks is following this well-known curve, while orbital time is following the linear scale on the bottom. The 4 breakup dates we've been discussing on the atomic clock are shown with a star on the curve here. However, using this curve, we can then correct the reading of atomic time to give actual orbital dates on our historical or biblical or archaeological calendar. This is explained in more detail at the close of the session on the Bible and geology. In that session, we show that the first breakup in the asteroid belt gave impactors that triggered the flood of Noah. The second breakup caused the biblical catastrophe of Babel, and the third coincided with the time of Peleg in Genesis 10:25, when the continents were divided. It is important to understand these dates coordinate with the oldest biblical text, the Alexandrian Septuagint, translated from the original Paleo-Hebrew about 282 BC. These dates do not coincide with the Masoretic text, which was put together in 100 AD. The early church fathers prior to 300 AD follow the Septuagint, as does the Eastern Church today. One final matter claims our attention. The breakup of the Kuiper Belt object sent debris into the inner solar system, and this debris took some considerable time to travel into the inner solar system. As you have a look at atomic time and convert it to orbital time, this period of time seems to be of the order of about 700 years or more. Now, the Kuiper Belt object also caused the breakup of the asteroid belt object, and as a consequence, this is a key event. This poses an interesting problem. As you look at the timing of this and the beginning of the created order, you find that this event of the breakup of the Kuiper Belt object is very, very close to the time when Adam and Eve sinned originally. As a consequence, you find what it says in Romans 8, that the whole created order was made to suffer because of man's sin. This is exemplified by the craters that we see right throughout our solar system. This is worth thinking about. Thank you very much for your time. I've appreciated your company. Blessings on you.